Let's now talk a bit about the storage slot allocation for mappings and dynamically sized arrays that is a bit more complex than their value type counterparts. These types are unpredictable in their dynamic size by definition, and because of that reason, the storage slots allocated for them cannot be reserved in between the slots for the state variables that surround them in the declaration order within their contract. Therefore, these are always considered to occupy a single slot that's 32 bytes in size with regard to the rules discussed so far, and their elements that they contain within that can change dynamically over the duration of the contract. Those elements, the storage slots for them, are stored in a totally different location, and the starting storage slot for those elements is computed using a Kachak 256 hash that we'll examine in the forthcoming slides. So for dynamic arrays, let's say that there is a state variable of dynamic array type, and based on the declaration order within that smart contract, let's say that this state variable of dynamic array type is assigned slot number P. This slot only stores the number of array elements within that state variable and is updated during the lifetime of the contract when this changes. The actual elements of the dynamic array itself are stored separately in different storage slots, and the starting slot for those elements is determined by taking a Kachak 256 hash of the slot number P. And those elements themselves, starting from that storage slot that we just calculated, are stored contiguously, and they can also share those storage slots if possible, depending on their types and depending on the size of those types. And if we have dynamic arrays that in turn have dynamic arrays within them, then the same set of rules apply recursively to determine their corresponding storage slots. This changes a bit when we look at mapping types. Mapping types, again, depending on the declaration order, if there is a state variable of mapping type and it gets assigned a slot number P, then that particular slot stores really nothing. It's an empty slot just assigned to that mapping. Compare this to the dynamic array that we just discussed, where this slot stores the number of those array elements. So in the case of mappings, there is no such concept. So this slot P stores nothing. It's just a blank slot that is allocated for this mapping. And the slots corresponding to the values for keys of this mapping type are calculated as follows. So for every key k, the slot that is allocated is determined by taking a Kachak 256 hash of h of k dot p. And what this signifies is that the dot is a concatenation of the two values of h of k and p. And we know that p is the slot number, which we mentioned earlier on. H is a function that is specific to the type of the key that we are talking about. And if this is a value type, then there is a padding that is done to make it up to 32 bytes. And if this is string or byte arrays, then H computes the Kachak 256 hash of the unpadded data. And the specific rules, the type specific rules that determine what H is, those details are have many nuances. So please take a look at the reference provided to understand what those are. So this should give you a high level understanding of the different types specifically the dynamic arrays and mappings that have more complex rules when it comes to what storage slots are reserved for them within the EVM, and how Solidity and specifically the declaration order determines the storage slots for all these various types. Let's now take a look at the storage layout for bytes and string. This has an interesting optimization. The storage layout for these types is very similar to arrays. So the actual storage slot, depending on the declaration order, stores the length of these types, and the elements themselves of the variable are stored separately in a storage slot that is determined by taking the Keccak 256 hash of the storage slot assigned to store the length. However, there is an interesting optimization. If the values of these variables are short, then instead of storing these elements separately, they are stored along with the length within the same storage slot. And the way this is done is, if the data is at most 31 bytes, then the first byte in the lowest order stores the value length into 2, and all the other bytes, the higher order bytes, store the elements that fit within the remaining 31 bytes. And if the length of the data is more than 31, so if it is 32 bytes or more, then the lowest order byte stores the value length into 2 plus 1, and the elements themselves, the data elements themselves, don't fit within this storage slot that stores the length. So they are stored separately, like we said, using the Keccak 256 hash of this slot's position. And the distinction of whether the values, the data values, are stored within the same storage slot as the length, or if they're stored separately, is made by looking at the lowest order bit. And if that is set, it means that they are stored separately. And if they're stored within the same slot as the length, then this bit will not be set. And this is because of the length being stored as length times 2 plus 1, or just length times 2. So this is an interesting fact that can be kept in mind when one is trying to evaluate the storage slots being used up for state variables that are of bytes or string types. So with this, we have touched upon the various EVM storage related aspects as they pertain to Solidity and their state variable declarations. Let's now move on to memory and see how some of the Solidity aspects map to the memory of the underlying EVM. To recall, EVM is a stack-based architecture. It has call data, it has the volatile memory, and finally the non-volatile storage. And EVM memory has a linear layout, which means that all the memory locations are stored linearly next to each other. And memory locations can be addressed at a byte level. The EVM instructions that are used to access memory are mload, mstore, that operate on the word size, that's 256 bits. And if one wants to store a single byte from the stack to memory, one can use the mstore 8 instruction. And again, all locations in memory are zero initialized. Let's take a bit of a deeper look into the memory layout of Solidity. Solidity places new memory objects at the free memory pointer. And all this memory that is allocated is never freed or deallocated. This free memory pointer in Solidity initially points to a hex value of 80. And we'll take a look at what is happening over there in the next slide. But all these concepts related to memory layout really matter from a security perspective only if the developer is manipulating this memory directly in the assembly language support provided by Solidity. Because if one is using Solidity as a high-level language without using assembly, then all this is automatically handled by the Solidity compiler itself. The initial value of the free memory pointer in Solidity is hex 80 because the first four 32-byte slots are reserved by Solidity, and these add up to 128 bytes and therefore the hex 80 value. The first two of those 32-byte slots are used by Solidity as a scratch space for the hashing methods. The third slot, again 32 bytes, is used for the free memory pointer. So this points to the next byte of memory within Solidity that is considered as free. Or in effect, this also indicates the amount of allocated memory currently within Solidity. The fourth such slot is referred to as a zero slot and is used by Solidity as an initial value for dynamic memory arrays. We'll talk about that shortly. And this again should never be written to. So these are the four reserved memory slots within the memory layout of Solidity. Let's now look into how memory arrays are allocated within Solidity. For memory arrays, every element in it within Solidity occupies 32 bytes. And this is something we mentioned in the context of the byte array and how every element occupying 32 bytes really wastes a lot of space despite the type of the memory array. This is not true for bytes and string types. And for multi-dimensional memory arrays, those are pointers to memory arrays. And for dynamic arrays, very similar to the storage, even within memory, these are stored by maintaining the length of the dynamic array in the first slot of that array within memory, followed by the array elements themselves. So these are some facts about how the layout is maintained for arrays within memory. Let's revisit the concept of the free memory pointer in Solidity. This pointer is maintained at position hex 40. And this is because the first two 32-byte slots are reserved for the hash function scratch space as we just talked about. And the initial value in the free memory pointer is hex 80, just beyond the reserved slots. And this pointer effectively points to memory that is allocatable in the context of Solidity at any point in time. And whenever memory is allocated by the compiler, it updates the free memory pointer. So these concepts should be familiar if you have looked at memory allocation of any other programming languages. And these just happen to be the specific ways in which Solidity handles memory allocation using the familiar concept of the free memory pointer and how it is updated upon allocation. With respect to zeroed memory or memory containing 0 bytes, there are no guarantees made by the Solidity compiler that the memory being allocated has not been used before. So one cannot assume that the memory contents contain 0 bytes. And the reason for this is there is no built-in mechanism to automatically release or free allocated memory in Solidity. And this, as you can imagine, has a security impact because if one is using memory allocated objects, and those are not guaranteed to be zeroed memory, then the default values may not be zeros. These again are relevant only if memory is being manipulated directly in assembly within Solidity, and these should not be much of a concern if one is not using assembly in Solidity. So with that, we have talked about the storage aspects and the memory aspects, the layout aspects specifically within EVM, and how they map to some of the Solidity concepts that we have talked about. Let's now talk about reserved keywords. These are keywords in Solidity that are reserved for future use. So they're not currently used by any of the syntax that is supported by Solidity, and these may be used for any anticipated new syntactic features within Solidity. There are many such reserved keywords. Some of them are after, alias, apply, auto, case, null, etc. And you can imagine why these could potentially be reserved, because they all have a specific significance in the context of programming languages or in the context of object-oriented programming languages. And Solidity anticipates that it may support features that may end up using these reserved keywords. An example of a keyword that was reserved earlier is unchecked, and this is now used as of version 0.8.0 for declaring any block within Solidity as being unchecked for arithmetic overflow and underflow checks. So we can assume that some of these reserved keywords might be supported in future Solidity versions for different features. Let's now talk about inline assembly and how that is supported by Solidity. Inline assembly is a way to access the Ethereum virtual machine features directly at a low level. And from a security perspective, this is important because it bypasses some of the safety features provided by Solidity at a high level language. Type safety is one such aspect. So if a developer is manipulating in inline assembly, then the corresponding code does not enjoy the type safety benefits provided by the Solidity compiler. And the language used by Solidity for inline assembly is called Yule. And this is somewhat of a recent feature. There have been a lot of developments in the inline assembly support by Solidity in the most recent versions, and this sees constant updates as you look at the most recent versions of Solidity. An inline assembly block is marked using the keyword assembly followed by the block itself within the curly brackets, and the code, the inline assembly code, is placed within the curly braces, and this code is specified in the Yule language that we just mentioned. Let's now take a look at some of the features supported by the Yule language. Yule supports assembly access to various features such as the external variables, functions, and libraries. Local variables of value type are directly usable in inline assembly. And local variables that refer to memory or call data evaluate to the variable address and not the value itself, effectively serving as a reference. For local storage variables or state variables that are also allocated in the storage, a single Yule identifier is not sufficient, because recall that storage has a concept of packing where multiple variables can share the same storage slot. Therefore, their address is in two parts. It refers to the slot and the offset within the slot. Assignments are possible to assembly language variables, which allow rich manipulation of these various variables within inline assembly. And one should take care when manipulating in this assembly language to remember that variables that point to memory or storage really change the pointer itself and not the data. And there are many other rules and restrictions, as you can imagine, when it comes to manipulating all these aspects within assembly as supported by you. Let's take a bit of a look at the syntax of the Yule language. Yule supports literals and calls. There are variable declarations that are possible in the form of let x colon equal to 7, which declares a new variable x and assigns an initial value of 7 to it. So these assignments are possible. There are scoping blocks that are supported by Yule so that multiple blocks can be considered within the assembly blocks. There is rich control flow that is supported using if, switch and for. There are also function definitions that are supported by Yule so that within inline assembly you can have multiple functions that help you modularize code written in that inline assembly. Take a look at the developments in the Yule language as supported by Solidity. This is happening at a great speed. There are a lot of features being added to provide a lot of richness and expressiveness by the Yule language for people, for developers who want to code directly in assembly. But like mentioned before, from a security perspective, this becomes even more critical than programming in Solidity itself, because inline assembly is typically considered as very close to the underlying virtual machine. So in this case, very close to the EVM. And if the internals of the EVM layout and all the nuances with respect to that are not paid attention to, then coding directly in Yule in the Solidity's assembly language might result in bugs, might result in some serious bugs where the manipulations are not done correctly and corruption happens, or maybe even vulnerabilities. So with that, we are done discussing a lot of the Solidity's features with respect to the high-level language, the storage layout, memory layouts, and the inline assembly support by the Yule language. Let's now take a look at the historical versions of Solidity, the critical versions, the breaking versions that give us insights as to how some of the features have evolved over time. And as mentioned much earlier on, Solidity, the development of the Solidity language is happening at a very fast pace. So a lot of these versions, the minor versions, the bug fixes happen on a monthly basis, and some of these breaking changes happen multiple times a year. And looking at some of these historical versions, the most recent ones at least, give a sense for what these breaking versions are, what some of the syntactic, semantic changes have been, and how those really have impacted the security of smart contracts written in Solidity. We will look at 3 sets of breaking changes with the Solidity compiler. Solidity version 0.6.0, 0.7.0, and then 0.8.0. Recall that breaking versions are versions that are not backwards compatible, or in other words, they've introduced significant changes to the syntax, to the underlying semantics that are not compatible with the previous changes. And these breaking versions increment the number that you see in the middle of the version. So for a Solidity version x.y.z, the next breaking version would be incrementing the y number. So that version would be x.y+1.z. So in Solidity 0.6.0, the previous versions were all in the 0.5.z series. With Solidity 0.6.0, a feature that was introduced was a breaking semantic feature. This changed the existing code, the behavior of the existing code without changing the syntax itself. And this was specifically related to the exponentiation and the type of the result. Until this version, the resulting type was the smallest type that could hold both the type of the base and the type of the exponent, the two parts of exponentiation. But with this change, the resulting type was always the type of the base. Solidity 0.6.0 also introduced 6 sets of explicitness requirements. Explicitness, as you can imagine, is good for security because it reduces ambiguity and any vulnerabilities that result because of that ambiguity. In this case, keywords virtual and override were introduced for functions in base and derived classes. Functions in base classes can now only be overridden when they're marked with the virtual keyword, and their corresponding overriding functions need to use the override keyword. Array length is read-only. It's no longer possible with version 6.0 to resize storage arrays by assigning a new value to their length. An abstract keyword was introduced for what became abstract contracts, or contracts where at least one function is not defined. Libraries have to implement all their functions, not only the internal ones as of this version. And there were various restrictions, explicitness restrictions brought forward for assembly variables. The other big change was state variable shadowing being removed. State variable shadowing is when you have state variables in the base contracts that are shadowed in the derived contracts, or the derived contracts have state variables with the same name as the base contract. This can be confusing, results in ambiguity, and have impacted the security of smart contracts. So with 0.6.0, this aspect of shadowing was not allowed henceforth. There were many other syntactic and semantic changes brought forward by Solidity 0.6.0. External function type conversions to address types are not allowed. Instead, they have an address member that allows similar functionality. Dynamic storage arrays for the push of X function on those arrays that until now return the length of the array, now return nothing. And until 0.6.0, there was a concept of unnamed functions. And this version split the functionality implemented by such a function into a fallback function and a separate receive function. These are two types of functions that we have discussed in the Solidity module. There are differences between these two functions and specific use cases where one of them is applicable versus the other. The receive function, for example, is called whenever the call data supplied is empty, and this is implicitly payable, whereas the fallback function is called when no other function matches. And the behavior of this also depends on if there is a receive function in that contract or not. and a fallback function can be made payable or not. If it is not payable, then transactions not matching any other function that send value will revert. So there are all these aspects that until 0.6.0 were combined under the concept of the unnamed function, but the functionality was split into the two different functions, fallback and receive, and some more aspects and features were made explicit to remove ambiguity and to provide additional control over how these functions manage different aspects. 0.6.0 also introduced several new features. The try-catch blocks for exception handling was introduced in this version. And this, if you recall, is used to react and handle failed external calls. Struct and enum types can be declared at a file level with this version. Until then, it was only at a contract level. Array slices can be used for call data arrays. NatSpec, as of this version, supports multiple return parameters for developer documentation. It enforces the same naming checks as the parent tag. Yule, the inline assembly language, introduced a new statement called leave to help exit the current function. And conversions from address type to address payable type are now possible via the payable primitive or directive, where X is of type address. So many new features, many explicitness requirements, many syntactic and semantic changes, and breaking changes as well introduced with the Solidity version 0.6.0. Let's now move on to the next breaking release, 0.7.0, and see what breaking semantic changes were introduced with this version. Exponentiation and shifts of literals by non-literals as of this version will always use uint 256 or signed int 256 to perform the operation as of this version. Until this version, the operation was performed using the type of the shift amount or the type of the exponent, which can be misleading. So this became very explicit. This again is a breaking semantic change because the behavior of exponentiation and shifts changed underneath without any changes to the syntactic aspect. This version also introduced several syntactic changes that could cause existing contracts to not compile anymore and therefore considered a breaking change. Examples of such changes were the syntax of specifying the gas and ether values applied during external calls that changed. The now keyword for time management within contracts was deprecated in favor of block.timestamp because now gave the perception that time could change within the context of a transaction, whereas it really is a property of the block correctly indicated by block.timestamp. The NatSpec aspect for variables was also changed to allow that for only public state variables and not for local or internal variables. GUI was declared as a keyword and therefore cannot be used for identifiers. String literals can contain only printable ASCII characters as of this version. Unicode string literals were also supported with the use of the Unicode prefix for such literals. The state mutability of functions during inheritance was also allowed to be restricted with this version. So functions with default state mutability can be overridden by pure and view functions, while view functions can be overridden by pure functions. There were also multiple changes introduced to the assembly support within Solidity. So many such syntactic changes were part of Solidity version 0.7.0.